everyone, today we are going to talk about lessons 15.1 and 15.2 in your Springboard book starting on page 199. I'm going to talk about them together because they kind of just play into each other. 15.1 sets up the problem and 15.2 talks a little bit more about the actual vocabulary and in context situations. So on page 199, what we see here is this bicycle problem. We have Stacy on her new bike, and her two big wheels of her bike have a 24-inch diameter, while her training wheels on it have a 6-inch diameter. And it takes her 4 seconds for this wheel to roll all the way around. So Stacy's basically riding this painstakingly slow. And what's happening is as she's riding, she's going down the street and there is some freshly painted parking stripe. And when she rolls over it, she's going to have basically this piece or this stripe, if you will, on her, or this paint on her tire that will eventually go around and around. Okay. So a couple of things with this. Again, the important thing here to note is that this front wheel is going to rotate once every 4 seconds. And if it's a 24-inch diameter, we're basically saying the radius of this circle is 12 inches around. Now, there is a 36-inch distance between the front tire and the training wheel. And then because the diameter is 6 inches on the training wheel, that means that each of the radii in that is 3 inches apiece. Okay, so if we think in the context of the situation, then if we were to graph this for the big wheel, let's focus on the big wheel first. We're starting here at 0. And the peak of this wheel, think about that paint splatter on the ground, the peak it's going to be off the ground is 24 inches. And again, it's going to repeat itself by the time we get to 4 seconds. So we're starting here on the ground. It will be halfway through at 12 inches, and then we'll move all the way up to 24 inches, and then back down here, right? So essentially what we would be seeing each time is with the big wheel, this idea that we're kind of, looping through, repeating itself, okay? Now, based on that 36-inch difference here then, and before the training wheel is going to hit the stripe, it's going to be, if we look at the circumferences of the two wheels, it's going to take a little bit longer time for the training wheel to hit that paint splatter, and it repeats every 1 second is going to be the revolution of that. So that's why we have this less here with the training wheel, okay? Now, again, that's kind of what the next piece then on page 200 talks about, is kind of that movement through. Now, the rest of this lesson basically then talks about finding the different heights using special right triangles with 30, 60, 90s to figure out how far off the ground the paint splatter is. And that's not as important to me in this lesson as if we jump to the very last page of this section, page 202, this check your understanding box, okay? Because basically the reason that we need to talk about this paint splatter idea here and these tire wheels rotating is the idea that this is a periodic function. That we have this graph that if Stacy keeps riding her bike beyond 8 seconds, we're going to see that continual pattern with the big wheel versus the training wheels, and that the pattern just keeps continuing. So when they talk about in question number 6, at what 3 other instances for the first 20 seconds is the spot going to be at the same position, again, we have to go back to the idea that this repeats itself every 4 seconds. So not only at time 2 is this paint splatter going to be the same height above the ground, but at time 6 seconds, and then 10 seconds, 14 seconds, and 18 seconds are going to allow for that same height because it keeps repeating itself. Because it's going to be the same height here every 4 seconds, right? It's going to continue on and on and on with that, okay? Now that then will lead us into then 15.2. So this is on page 205. So again, we're talking about this idea, this recall here of these different graphs, right? And that periodic nature about them, how they're repeating every 4 seconds and every 1 second. Now the next piece of this then, beyond page 203, on page 204, asks us to change some features about our bike that would ultimately change the graph, okay? So the original graph of Stacy's bike again looks like this, where we are peaking at 24 down here, peaking at 24 down here, right? We have this kind of general curved look to our graph, okay? If we change the diameter of her bike from being 24 inches to only 18 inches, how is this affecting our graph? Well, it's affecting the overall peak, right? Because if all we're changing is this peak here, instead of peaking at 24, our graph is now going to peak at 18. And instead of the midpoint here, or the mid region of this, like halfway through, going to be 9 inches or 12 inches above the ground, it's now going to only be 9 inches of the ground. So our transformed graph here would look like so. Okay. Now the next piece of this then asks us on page, the bottom part of page 204, says then that what we're going to do is we are going to change this so that instead of the wheel rotating every 4 seconds, it's now rotating every 3 seconds. So Stacy's pedaling a little bit faster. So she originally looked like this, but now she's going to repeat quicker. So we now need to have this repeat by the time she hits 3 seconds. So at the halfway point is going to be 1.5 seconds. And then again, she's going to repeat by 6. So again, the halfway between there at 4.5 seconds. And then again, it would kind of be out here would be this pattern. So again, she's repeating a little bit quicker, which ultimately means that we're seeing these hills occur closer together. Okay, so they're going to be repeating more often and closer together. All right, this next piece then accounts for some visuals. So it's all about how we're talking about the distance above the ground. So far, we've always started at 0 here with this bike wheel. And then moved along. But what if we considered that the midline here is now 0? And pretty soon, like if we started here on the bike is our first part. So then, you know, second number 1, we're up here 12 inches above the ground because we're back to a 24-inch diameter. And then halfway through, we're back down here. And then we're down here, officially kind of like at the idea of negative 12. And then back to the beginning. So instead of starting on the ground at 0, we're kind of looking at it this way, like we're starting here on the bike. Okay, so basically what's happening, if we were to sketch this graph, again, instead of starting at 0 and going up, we're starting at 0 and going up to just 12 at second 1, second 2 back down to 0, second 3 we're down to negative 12. And then by second 4, we're back to 0. So our graph instead would be here, starting on the ground now, is here, up here, up here. So we're counting that as negative 12 is like our starting on this wheel. Okay, so really our graph would now look like this, AKA it would be a shift down from what we have. Okay, so, excuse me, we're still starting with the wheel on the ground. We're still starting here at negative 12. I do not mean to confuse you. But then as we're rotating around, we're rotating up this way. So this would be our shift here, down. All right, and then last but not least on page 205, we shift about, this is where I was talking about if we shifted looking now instead at the smaller training wheel as actually being the starting one, what happened to our graph? Well, it looks like it appeared to have moved, 2 seconds to the left, right? Everything kind of shifted over based on that, so that this is now the starting spot. So everything kind of shifted. So the reason that we are looking at these graphs is because all of them are examples of changing different aspects of our periodic function. Okay, and a periodic function is that repetitive nature that we're seeing in these graphs over and over and over again. And the period is the amount of time it takes that function to repeat itself one full rotation through. The amplitude is basically looking at the distance between the max and the min divided by 2. That would be your amplitude of your function, so kind of how far off a midline of your function you're moving. And then a phase shift is just the fancy way of saying a horizontal translation of your periodic function. So each of these graphs was an example of each of these. This first one changed the amplitude. This first one here, actually the graph that they're talking about here on this one wasn't the amplitude. This one was an example of changing the period, because our original graph went from here to here, and then we made the full rotation 1 second shorter. So what we did was we changed our period. And basically what happened was, in the original graph, it was periodic because the original graph was the same once we got to x plus 4, right? That shift over here. Now we changed it so that it repeats quicker. It's repeating by the time it gets to x plus 3 is when it's back to the starting spot, 3 units to the right here. Okay, or 3 units to the left for that matter. The next piece of this then, this is the one, this was the very first one we did. This is where we changed the amplitude, because we changed our amplitude from being 12 to just being 9. So again, we have to be careful. The amplitude is always where's kind of our midline. So in the original graph, the amplitude was 12, right? That's like halfway between here. They went 12 units up, 12 units down from its midline. And then in the transformed graph from here to here, our midline shifted down a little bit because this is now 9 and 9. So we changed the amplitude from 12 to 9. The next graph then, part C here, talked about the vertical translation. We shifted it down 12 units. So that was back in this particular graph. This was our original graph, just shifted down. And then last but not least, we also had that phase shift where we moved everything to the left about 2 seconds, right? So that we could start it a little bit. It was the same graph, just shifted to the left. Now, last but not least, again, looking at some of the things you're going to have to do with delta math, or just looking in general with these equations, what do I want you to get out of this lesson? Well, one thing you want to be able to do is look at a graph and tell what is the amplitude and what is the period. Now, again, your amplitude is half your distance, right, from max to min. So in this case, it's like we have a midline right now at y equals 0. It's kind of that midline point. And notice with the scale on our graph, we went 3 units up and 3 units below that. So the amplitude, again, is half of that distance of 6, aka the 3. Okay. Now the period then is how long does it take this graph to repeat itself. So in this case, you always kind of want to look at like a good starting and stopping location. So here, if we just look at the graph, starting on that midline, we went up, down, back to the beginning, right? One full revolution through, up, down, back to the beginning, not just back to the starting point, one full revolution down to the minimum as well. That took 10 seconds, I guess, in the context of the problem, but this just took 10 units to repeat itself. So the period is every 10 units, it's going to repeat itself, okay? Now also dealing with the period is this piece here, okay? Because if we look back at the problem we were talking about on the last page, we said, okay, the original it took to repeat itself, it was back to the original location, x plus 4. Or for the transformed function here, was x plus 3 because it repeated after 3. So when they're just telling you this piece here, what does this imply about the function? Well, it's saying that it's back to its original position here when you get to 10. So what this is basically saying is that this periodic function has a period of 10, right, that it's repeating itself again. Definitely will be working more with these vocabulary words, especially moving forward. Thanks everyone for watching.